In this video, we're going to explain the concept of maximum likelihood estimation. We're going to do this with an example. When we study viruses, we many times try to find characteristics of, for example, its genome that can help us maybe attack it or identify it. Here's an example where we took a virus, we looked at its genome, and we looked for palindromes. So the data that you see in this figure is coming from little segments of 4,000 base pairs, and we count the number of palindromes in each one. We notice that there's a specific location where we see 14 palindromes, and we wonder if this is higher than expected. Maybe there's something special about this region that we can use in some practical way. But in general, all we're trying to do right now is determine if 14 is higher than expected. Now, to define higher than expected, we need a statistical model. What would we expect to see by chance? So here, the Poisson model seems appropriate. We're counting rare events, which is precisely where the Poisson approximation is useful. So here's the data. Here are the counts of palindromes for these segments, and you can see it does look like it follows a Poisson distribution, just roughly based on this histogram. So we're going to make that assumption. We're going to assume that under the null, the number of palindromes in each segment follows a Poisson distribution. And then we can ask, what's the probability of seeing a 14? But we're missing one thing. We don't know the rate. We don't know what lambda is. So here's where maximum likelihood estimation comes in. The idea is that we have data. In this slide, we represent the data with x1 through xn. These would be the counts at each of the segments. And we've observed certain numbers. So what we can do is we can write out the likelihood. So what's the probability of observing x1 equals to k1, x2 equals to k2, all the way up to xn equals to kn, the data that we saw, for a particular lambda. We can compute that. And there's the equation for what that is. So in the bottom equation, we write out what is called the likelihood. We write that function as a function of lambda. And now we've rewritten it so that we have the exponentiated log likelihood. The log likelihood is a sum, which is easier to work with on computers. And what we're going to try to do now is find the lambda that maximizes this likelihood. What is a lambda that makes the likelihood highest, that makes the likelihood of the data we saw the highest? This is intuitive that we would want to use this lambda. It's the lambda that we could say is the lambda that best fits our data. So here is a piece of code that writes down the likelihood and then uses an R command optim to find its maximum. On the right, we see a figure that would be the likelihood function. We see different values for different lambdas. It forms a function, and you can see the maximum. It's somewhere around 5. In the case of the Poisson, the maximum likelihood estimate turns out to just be the average of the data, in this case, the counts. But we show this as an illustration, generally, how we compute maximum likelihood estimates. All right, so we find that lambda is about 5.1. If we use this lambda and make a QQ plot, something like a QQ plot, we see that the data fit the model very well. This is real data from a real virus, and it fits very well. So now, to answer the question that we originally asked, what's the probability of seeing something as big as a 14 when the null says it's a Poisson model with a certain rate? And here we see that it's a very small number, it's 0.0007. Now we looked at 57 counts, so we have to do some kind of multiple comparison correction. If we use the Bonferroni, if we're conservative and use the Bonferroni cutoff, we see that we are, in fact, barely significant. And this would be a result that might be worth reporting as interesting, biologically interesting. So we have seen how useful models can be, and also we have seen what maximum likelihood estimation is and how we apply it.